I'm Dr. Maria Weber, and I'm an assistant professor of physics at Delta State University, and I want to talk about drag forces. Drag forces are resistive forces, so they always oppose the motion of an object. They always oppose the direction of motion of the object. Drag forces occur on an object when it's moving in a fluid. And fluids can be gases like the air surrounding us, or it could be liquid like if you're moving through water. Now the magnitude of the drag force is proportional to the square of the speed of the object. So if we write that down as an equation, we have that the drag force is equal to 1/2 times the drag coefficient C times rho, which is the density of the fluid that the object is moving through, times A, that's the area of the object that's facing the fluid in the direction of motion, times velocity of, or times speed actually, this V represents speed, times the speed of the object moving through the surrounding fluid, which could be air or water. And so this is our equation for the drag force. Now, typical values of the drag coefficient C here can range from about 0.4 to 1. And the drag coefficient varies based on the shape of the object, and it can also vary according to the speed of the object or properties of the surrounding fluid within which the object is moving. So generally, C, the drag coefficient here, must be solved experimentally. Right, so let's demonstrate drag forces right here. So here I have my Play-Doh object here, and I have a styrofoam cup. Now in the absence of air in a vacuum, regardless of the masses of these objects, they should fall towards the ground. If I drop them from the same height, the time they should take to fall to the ground should be the same. But because of drag, this object, my styrofoam cup, is going to take a little bit longer to fall to the ground than my Play-Doh ball here. So let's see. If I hold them both up right here and drop them. So maybe you didn't see it fall all the way down to the ground, but what happened was that the Play-Doh ball fell first and the styrofoam cup took a longer time to fall to the ground. That's because this object, the styrofoam object, has a larger drag force acting on it than my Play-Doh ball here, okay? And we can relate that to the fact that, well, both of these objects have a different drag coefficient. They both have different shapes. And also, they both have different cross-sectional areas. The area that's exposed to the surrounding fluid as they fall toward the ground. And so those both contribute to the different drag forces that are acting on these objects as they fall, which changes the time it takes them to reach the ground. So when an object falls from rest, the drag force is directed opposite its direction of motion. So if we have an object here, like my Play-Doh ball, and I drop it from rest, well, first of all, we're going to draw the free body diagram of that Play-Doh ball. It has its weight acting downward, its mass times gravity. Then it has its drag force acting upward here. And so the magnitude of this drag force gradually increases from 0 as the speed of the body, the falling body increases as it starts to spend a longer time falling toward the ground. So let's go ahead and use F equals ma on this free body diagram right here. So if we do the sum of the forces in the y direction and set that equal to mass times acceleration in the y direction, we have the drag force from the object acting upward, Fd. We have the weight of the object acting downward, so that would be minus mg is equal to the mass of the body times its acceleration. And so if the body, the object here, falls long enough, the drag force right here eventually equals the weight of the object. And in that case, if the drag force eventually equals the weight of the object, then both of those terms cancel each other, which means that the acceleration of the object becomes 0. And so the body's speed no longer increases. The object's speed no longer increases. Because if you have a constant speed, you have a 0 acceleration. So over time, the acceleration of the object will become 0 as the drag force increases such that eventually it will equal the mass times gravity. So let's go ahead and say that that is equal to 0 there. And so if we do that, then we have that the drag force, which I'm going to say is 1/2 c rho a v squared, is equal to the object's mass times its gravity. And so if I solve this equation for a velocity, then eventually I find that the velocity, what we will call the terminal velocity of the object, is equal to the square root of 2 times its mass times gravity divided by the coefficient, the drag coefficient, times density of the surrounding air times the area of the object that's facing the direction in which it's falling or moving. And so this is the terminal velocity, the velocity that this object must achieve in order that its drag force equals its mass times gravity. And if that happens, then the object is no longer accelerating. It has reached a constant velocity, which we call the terminal velocity here. Okay, so I've gone ahead and I've rewritten my terminal velocity equation just in a different space on my board, and I want to solve a quick sample problem. So suppose you have a cat, and this cat falls from a really high height, maybe it's on top of a really tall building, and that cat falls off the side of the building. Oh, sorry, cat. And eventually the cat reaches a terminal speed that we'll call pretty fast terminal speed of 100 kilometers per hour, while it's kind of like got its legs in, it's sort of tucked up kind of like a little ball while it's falling. But as it's falling, it eventually stretches out. It stretches out its legs, and that doubles its area. That doubles its cross-sectional area that is exposed to the fluid, to the air as it's falling downward. So then, let's call eventually A becomes 2A. How fast is the cat falling now when it reaches its new terminal speed once it stretches out and doubles its cross-sectional area? So the only thing that changes between these two different situations, the cat was initially curled up in a ball, but then it spreads out and it increases its cross-sectional area. So that's the area of the cat perpendicular to its falling motion. So let's set up a ratio of the terminal velocity of the cat, let's call it the new terminal velocity of the cat with the sub n, divided by the initial terminal velocity of the cat, or the original terminal velocity of the cat, which I'll call v sub to. And so we'll set that equal to, here we've got on top 2 mass times gravity of the cat divided by c rho times 2a, 2 times the area, 2, it increased its area by 2, and a factor of 2. And then on the bottom we have the square root of 2mg over c rho just times a. And so a lot of things in this equation are going to cancel here. So these, the 2 times m times g cancel on top and bottom. The drag coefficient and the density cancel on the top and on the bottom. So what I'm left with then is, on top I have 1 over the square root of 2a, and on the bottom I have 1 over the square root of a. So I'm dividing by a fraction, which is the same thing as multiplying by the reciprocal. So this is the same thing as 1 over the square root of 2a times the square root of a over, square root of a over 1. Okay? And so both of these square roots of a on top and bottom. Those cancel, and then I'm left just with the ratio of the new terminal velocity of the cat to the original terminal velocity of the cat is 1 over the square root of 2. Okay. So the new terminal velocity of the cat is going to be its original terminal velocity times 1 over the square root of 2. So Vt new is going to be equal to 1 over the square root of 2 times the original terminal velocity of the cat. So by just spreading itself out, the cat has increased its cross-sectional area that's exposed to the fluid as it's falling downward, the surrounding air as it's falling downward. And so that creates a situation where the cat now has a slower terminal velocity. A similar thing happens, for instance, when you're skydiving. When you're skydiving,